Hello and welcome to 6.2 Disk Method and Washer Method. This is AP Calculus. My name is Mr. Green, your teacher. Today what we're going to do is we're going to spin things really fast. Doesn't actually matter if it's fast, but we're going to spin things to create volumes. It's going to be great. And then if you can't visualize what that means, let me show you. Here's an example that's used frequently. It's called a lathe. So here's a video that I would show you in class if we were in class. But basically what you do is you spin something really fast, and then you can create a 3D shape out of it. See how this one cutter is creating this cylinder in this case. We can do really cool stuff with that. This is another boring example, but still spinning things to create another shape. And that's like the theme of today. We're going to spin things to create another shape. So this is a cool one. Look how cool that is. And this is called a lathe. And this is what we're going to do. We're going to find the volumes of these cool shapes today. Now there's quite a bit of reading and things that we have to do to get this out of the way. So if a region in the plane is revolved about a line, the resulting solid is a solid of revolution. So when you rotate something around a line, it's called a solid of revolution, and the line is called the axis of revolution. So here's what we got. So we're taking this line right here, we're revolving it around here, and we get this nice disk. The simplest such solid is a right circular cylinder or disk. So this is the most simple thing that we can make by rotating it around the axis of revolution, which is formed by revolving a rectangle around the x-axis adjacent to one side of the rectangle. The volume of such a disk is equal to the area of the disk times the width of the disk. Can you think about how to find the area of the disk? So I couldn't get my pen to work, but now it works, so I just wrote the answer. So what we got is this area of the disk, which is just pi r squared, simple circle, area of the circle, and then times the width. So that's the volume. So that's great, where r is the radius of the disk and w is the width. To see how to use the volume of a disk to find the volume of a general solid of revolution, consider a solid of revolution formed by revolving the plane of the region of the figure about the indicated axis. So if you look at this, we got a curve now, and we're going to fill it up with disks, and then we're going to rotate all of them. And the more rectangles we use, the closer and closer our volume gets to the actual volume. Thus, we can use the concept of the integral to find the volume of the solid revolution. Isn't that great? As a brief side note, every single textbook I've ever seen that teaches this concept always uses these exact same graphics that I have here, so I decided to use them as well. Yeah, it's weird that different textbooks have these exact same graphics, but you know, whatever. So here is the disk method. So here's the formula that you knew. This is just of the disk, and then we're going to take it and we're going to get the delta volume, or the change in each one of these disks, and that's how you get the volume of each one of these disks. And then if you take the volume is going to equal to pi times the integral from a to b of the radius, which is a function, squared dx. Notice that the width is represented here by an integral. To the disk method, that's what we're going to use. So that's what we just showed you. To find the volume of a solid revolution in the disk method, use one of the following formulas below. So if you have a horizontal axis of revolution, that means this way. So you're rotating this shape like this. It's really hard for me to draw these. Then you're going to use this formula. Notice that it's r of x. So that means that this formula is in terms of x. And then if you have it this way, you're rotating it like that, then notice that the vertical axis of rotation, you have a function that is in terms of y. Now, I put this here so you guys can kind of remember, and then remember that the delta x is what's increasing, so that's why that goes there, and the delta y is what's increasing and decreasing, and so that's what goes there. That's another way that you can kind of remember which variable you have to use when you're rotating these. Just remember, use x's when you're rotating this way, and y's when you're rotating this way. Now, I made a video representation of this because it's really hard to see on 2D paper, so I'm going to put the link right here. Go ahead and click on it and watch this. It's 2 minutes. It's really fast. I just used a program called Fusion 360. You'll see. Go watch it, and then we'll try some questions. So now that you're back from the video, let's find the volume of a solid formed by revolving the region bound by the graph of f of x is equal to square root of x and the x-axis from 0 to 9 and the x-axis. Great. So this is the exact thing that I just had modeled in Fusion 360. So if we were going to do a quick sketch, it would look like this, and we'd be rotating it like this. So our final shape would look kind of like this. And that's, here's 9, let's see. So what we have to do is, because we're rotating it around this axis, and our x's are what's increasing, that means we're going to need this thing to be in terms of x. So our volume on this case will be pi times the integral from 0 to 9 of our function, because our function will give us the radius, which is the square root of x squared dx. Now notice that I have multiple different radiuses. If I go along here, the radius is continuously increasing because it's this function, square root of x. So I have infinitely many radiuses that I'm adding up to get the volume. So cool, right? So let's go ahead and simplify this and then make it a nice happy little integral. The square root of x, that's just x dx. That's great. So go ahead and calculate this and I'll come back with my answer. Alright, I'm back with my answer. I got 81 pi over 2. I thought that was a great question. Now, what I'd like you guys to do is go ahead and try to set this next one up, and I'll come back with my setup, and then I'll work through. Alright, so I noticed that my increments that were increasing were y values. So then I noticed that I needed a dy, so I solved this function for y, and then I knew it was the positive value. It actually won't matter if you did plus or minus in this case, but it usually would, because I'm squaring both sides. And then I got 4 minus y, the square root of it, all squared, so then I can just calculate that interval. So I'll invite you to do that now, and come back and check your answers. Okay, so that's what I got. I got 8 pi. Now notice I don't have units here because there are no units. If there were any units given, I would have the volume and whatever the units were cubed. So much fun. Okay, now we've got another question right here, and I've got this beautiful drawing of it for you. Find the volume of the solid formed by revolving the region bounded by the graph of the square root of sine of x and the x-axis from 0 to pi about the x-axis. So we're taking it around here, and this is the shape we're going to get. What I'd like you to do is try this entire question, and I'll be right back with my answer. Okay, so I have my setup. Notice that my increments are increasing in the x direction, so I needed x's in my function. And I set it up, squared it, cosine, I got 2 pi. Pretty cool stuff, right? Okay, now, find the volume of the solid formed by revolving the region bounded by the graph of f of x equals x cubed and the y-axis from 0 to 8 about the y-axis. Now, I'm pretty sure I messed this up, and that should have been a y right here, but let's try it out. Go ahead and see if you can set this up. Watch out for that x. Let's do it as is. Yep, looks like I probably messed this question up, but anyway, let's do it as it is. So this is the solid that we're going to be revolving around the y-axis, and notice that it'll go from 0 to 512. Holy smokes, that ended up with a big old number, didn't it? Because we had to plug 512 into this, and whoa. Anyway, I thought that was a fun question, even though I probably messed it up. I should probably have made that a y. The question would have been much easier, because it would have been from 0 to 8. But anyway, doesn't matter. I thought it was fun. Now, we are going to do it when there's a hole in the middle. So it's the exact same process, but sometimes it's not. You'll see. Here is a quizzes or something that I put here. You can practice that. We don't have time in class today. Well, if we were in person, we'd do it. But anyway, the disk method can be extended to cover solids of revolution with holes by replacing the representative disk with the representative washer. Every year that I teach this, students are like, Mr. Green, what in the world is a washer? So I looked it up, and I can show you a picture. So what a washer is it's just a disc with a hole in the middle. So notice that it's just a disc with a hole in the middle, and what you use them for is you use them to bolt on something so that the bolt doesn't apply too much pressure. It kind of spreads out the pressure, but that doesn't really, how it's used doesn't matter for us. All that matters is it's a disc with a hole in the middle. That's a washer. That's why this is called the washer method, because when we have something that we're going to revolve around a line that has a gap in between what we're revolving and the line, there's going to be a hole in the middle. So that's exactly what it means. And what you can do is the exact same thing as last lesson, where you took the volumes and you subtracted out the part you didn't need. The areas, and you subtracted out the area you didn't need. We're going to do the same thing here. So the way that we do this is we just take pi times the big radius minus the little radius, and we square them, and then you have the w. It's possible to do this in two different things, but we just mathematiced it and made it nice and good looking. This is the exact same thing. So it's the volume of the whole thing minus the volume of the little thing. They just factored it so your life is easier. But that doesn't matter at all. So, to see how this concept can be used to find the volume of a solid of revolution, consider the region bounded. So here it is. You have a big radius, which is this function, and a little radius, which is this function. And when you revolve it, you get something crazy looking like that. So let's go ahead and try that out. Let's visualize this really quick. So let's take a look, and you will see that I have these discs, and I'm making a solid out of them. So we're rotating these around, rotating it around, rotating it around, and rotating it around the last time. And then we make it a full revolution to make a solid with some kind of hole in the middle. And this is just an approximation, of course. But that's it. That's all we're going to be doing. And it looks terrifying, don't worry. So, find the volume of a solid formed by revolving the region bounded by the graph of f of x equals x and the x-axis about the x-axis. So that's a review question. Do that real quick. Go! Okay, so I did that one and I got pi over 3. Now, go ahead and try this review question. We're just doing this, by the way. And then we're going to find the volume of a solid formed by revolving the region bounded by the graph of f of x equals x squared and the x-axis, and 0 to 1 about the x-axis. So go ahead and try this question now. Okay, doing that one, I got pi over 5. Now, what we're going to do is we're going to find the volume of the solid formed by revolving the region bounded by the graphs of y equals x, this one, and at y equals x squared about the x-axis. So we know that the answer is just going to be this minus this, and we'll be done. But let's go ahead and show you how we can do that using all of the math. So we know that the y equals x is on the top and this one's underneath. So what we're going to have is we're going to have pi times the integral from 0 to 1 of x squared minus x squared dx. And we know that when we take this integral, we get pi over 3 minus pi over 5. And then we can just simplify that down. And we get 2 pi over 15. So that is the washer method. And here's the actual formula for it. It's just what we already know. You just take the volume you need, and to take the volume of the big one, and subtract out the volume of the little one, and that's how you get it. You could do this as two separate integrals if you really wanted, but it's easier if you just do it as one, and remember that this integral represents the width. So, here is a real question right here. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. So we're going about the x-axis, so we got delta x. Here's the square root of x, so that's the one on top. And here is x squared, so that's the one on the bottom. Go ahead and try this question, and I will be back with my solution. Alright, so I got 7 pi over 10. I think it's pretty great. Now, on these next questions, you could do them if you want, but I just want to do the setup and then just be done with it. And we'll finish these notes. I feel like we've done enough practice questions for you guys to do your practice today. So, in these ones, just set it up. You don't have to do it. Go ahead and try 5 and 6. See if you can get these setups. Once again, you don't have to try these ones. And then I'll be back with my solutions. Okay, so here's my setups. X squared is the one on top, so I squared it, and x to the 5th is on the bottom, so I had to square that second. Notice on this next one, the one in the top is this 4 minus x squared over 4, and that whole thing has to be squared. So watch out for that. If there's a term that has a plus or minus, you have to square the entire thing, and then you just subtract the one underneath, which is just y equals 2, and it is 2. There's a couple different ways I could have done this, because this is an even function. I could have put a 2 here, and then from 0 to 3, probably would have made my life a whole lot easier. Here's some more practice questions that you can do. I'm not going to ask you to do them because you have a worksheet for practice. Isn't that exciting? Woohoo! So go ahead and go work on your practice. You can try these extra questions if you want for practice, but I'm not going to assign them. Have a wonderful day. Let me know what questions you have.